Okay, Calc, this is the second half of section 2.3. We are on, I think yesterday we left off with example 4. So now we're on to example 5, and we're just kind of going through the, I guess, like the cheating method of finding a derivative. And now they're going to start to do like longer equations. Okay, not anything too crazy. All you're going to do is just each piece individually. But now it's just kind of shoved all together in one polynomial. But the same rules apply. Let's start with example 5. This one, the first one, isn't terribly difficult. The bottom one is kind of gets a little ugly, but this one, if you are taking the derivative, let's just start with the 2x to the 6th power. 6 comes down in front, multiplies by 2. That's 12x to the 5th power. And then same thing here with the 9. I'm going to bump the negative 9 down in front, so minus 9x to the negative 10th power. Okay, I have a lot of people that like when we're, subtracting from exponents, they're like, oh, negative 8, because 8 is smaller than 9. Well, since the 9 is already negative when you're subtracting 1, that makes negative 10. Okay, and the only other thing that I would do to fix him is bump this x down to the bottom. Okay, now, when we go to do this, I've seen everything under the sun that is wrong, right? Like I've seen this happen. That is not correct, right? This is one term. This is another term separated by a minus. So when I move that x down to the bottom, he only goes below the 9, right? This is incorrect, okay? So be careful of that because we have like things that are trapped. These are two separate terms. Minus in between them, 9 over x to the 10th power. So be careful how you're simplifying. That is what he should look like, okay, for his derivative. All right, now let's talk this ugly one. Okay, we are dividing by the square root of x. All right, so I gotta think how I want to address this. Well, okay, so here's one way to look at this. I'll address it two different ways, right? I have the square root of x minus 2x. And what I can do is I can separate those into two pieces where I have this thing going on, right? Okay, and this left side, he's going to reduce to 1, right? The square root of x over the square root of x is just 1, okay? And then we can take the derivative of 1 and all the things, right? But then we still have this ugly thing going on over here, okay? So what I'm going to do is I'm going to take this x, actually, let's take this x and write it as x to the 1/2 power because that's what he is, right? Square root of x is x to the 1/2 power. If I move him to the top, he is x to the negative 1/2 power, okay? And when I try to combine him with this x, I add the exponents, right? X to the 1st power, x to the negative 1/2 power. When I add those exponents together, I get 2x to the 1/2 power, right? Okay, so now what I'm looking at is 1 minus 2x to the 1/2 power, and now I'm taking the derivative of him, right? So the derivative of 1 comes out to be 0. The derivative of this thing, I'm going to take the 1/2, I'm going to bump it down in front, right? So 2 times 1/2 is negative 1. X to the, if I subtract 1 from the exponent, 1/2 minus 1 is to the negative 1/2 power. Okay, now he can go back down underneath to make him a positive 1/2 power, all right? So this 0 is not doing anything. I can put the negative 1 on top, x to the 1/2 power, or another way of writing that is the square root of x. And that's what he will look like, okay? Don't worry about the fact that the square root is in the bottom. We don't care about rationalizing the denominator for right now, okay? We'll leave it like that, okay? So that was kind of ugly. Now you could have, if you wanted to, written this top as x to the 1/2 power minus 2x, right? The top is that. On the bottom, he's x to the 1/2 power, right? But if I move that to the top, he is x to the minus 1/2 power, and then I distribute this thing through. And when I do that, I add the exponents again. So I have 1/2 and negative 1/2, which is x to the 0 power, which reduced to be 1 like it did over here, right? Okay, so that's another way of looking at it. If you don't want to separate it into the two pieces, you could just move him up to begin with and then distribute him through. And you will get the same simplification to this guy over here before we take the derivative, okay? All right, that one was kind of messy. The hardest part of most of this stuff is like the algebra and the simplifying and the doing the things and the doing the exponents and that stuff, even before you take the derivative. The derivative is the easy part, right? All right, let's go over to example 6. Now we have this thing. It is asking for to find dy dx, okay? But if you remember from what I said yesterday, finding the derivative, differentiate, find f prime, find y prime, find dy dx, find the slope of the tangent line, or doing the limit process, that's all saying the same thing. They're just asking you to find the derivative. Okay, so dy dx, this is my function, and I have 4 terms there, so I'm just going to do each term individually.
Mommy.
So again, what's up?
When I brush my teeth, then am I going to drink some water?
You can drink some water and go brush your teeth, okay? And then you'll be done.
But when I brush my teeth first, and then...
Can you have a drink of water?
Yes.
You can drink water.
Yes. Yes.
Okay, let's go.
All right, so
You don't have to brush.
this term, I'm going to take the 8, I'm going to move it down in front,
You want to brush?
and 8 times 3 is 24, and 24x to the 7th power. Okay, and then I'm just going to keep going from there. Minus 5 comes down in front, 5 times 2 is 10, x to the 4th power. Okay, this is x to the 1st power, so the 1 comes down in front. This is 1 times 6, which is 6x to the 0 power, right? And x to the 0 power is 1, so this really just goes away, right? We know that if it's like any number times x, the derivative is just going to be that number. And then the derivative of a constant, the derivative of 1, is going to be 0, because this is like x to the 0 power. 0 comes down in front, 0 times 1, that just knocks that whole term out, right? So this is going to be my derivative, and they will label that as dy dx. Or sometimes they'll call it, I kind of like to use the, this symbol, y prime. Okay, since he's called y prime is what we call him for his derivative. But that's kind of how he works. Okay? Okay. Next. All right. Here we go. This is getting into a little bit of what we're going to see going forward, like into the coming chapters, right? At what points, if any, does the graph of this function have a horizontal tangent line? All right. I give you the graph on your homework assignment. You won't be given the graph, but we can see from here that he does in fact have a horizontal tangent line here, right, where he just like touches and grazes to go off, and a horizontal tangent line there, right? He has a high and a low point, and both of those places have a horizontal tangent line. Now, to figure that out, if I'm looking for a horizontal tangent line, I'm looking for the derivative is equal to the slope of the tangent line. So if I'm looking for a horizontal tangent line, my slope is going to be 0. So in other words, I want my derivative, or the slope of the tangent line, to be 0. I want to set my derivative equal to 0 and find where those places are, right? Again, horizontal tangent line means that I'm going to have a horizontal line which has a slope of 0. Derivative is slope of tangent line. I want that to be 0, right? So all I'm going to do is I'm going to take this guy, I'm going to find his derivative, I'm going to set him equal to 0, and find where these 2 points are, all right? So derivative of this guy, let's see if we can get a little faster. 3 comes down in front. This is 3x squared, okay? The x, if we have a constant times just an x, okay, that's to the 1st power. The 1 comes down in front, all the things, right? It's just minus 3, right? And he is now equal to 0. I want to set the derivative, which is this guy, equal to 0 to find where those horizontal tangent lines are, because that's where the slope, the m, is 0, right? All right, and then I just solve. So I'm going to add the 3 over. 3x squared equals 3. I'm going to divide both sides by 3. And I have x squared equals 1. And then I'm going to take the square root. And since we put the square root in there, I have a x coordinate that is positive 1 and negative 1, right? The square root of 1 is 1, but it's plus and minus. So I have 2 places where I am going to have a horizontal tangent line. One place is at 1 and one place is at negative 1, right? 1 is here and negative 1 is over here, but I don't have the y coordinate for those. How do I find the y coordinate if I have the x coordinate right here? Like, I know the x's are negative 1 and positive 1, but how to find the y coordinate? Plug them into the original function, right? That'll give you y. So if I plug 1 in here, 1 cubed is 1, minus 3 times 1 is negative 3, plus 4. 1 minus 3 plus 4 is 2. So 1 comma 2 is going to be where I have a horizontal tangent line. All right. Now here we go. The next one, if I plug negative 1 in, negative 1 cubed is negative 1. Negative 3 times negative 1 is plus 3, plus 4. That is going to be at 6, right? So those are my two places where I'm going to have horizontal tangent lines. Now, why is this important? Why is this helpful? You will have a horizontal tangent line at every hill or valley on a polynomial function, right? So if I take the derivative and I set it equal to 0, I can find any maxes or mins of a poly function. That is so helpful. I can find where the maximum, where the high points are, where the low points are, right? So like when I'm talking about like, let's say this polynomial function is representing, I don't know, like my production of a certain item that I'm selling, right? So like I'm increasing production, I'm decreasing production, all that stuff. I can figure out where the maximum production is happening by taking that, they call this a modeled equation, right? Like the equation that models my production. That's kind of like a line of best fit, but it's a cubic function for your line of best fit type of thing. And your computer spits out that function, and you can do the derivative, set it equal to 0, and it will tell you where in time that maximum point or minimum point occurred, right? So super helpful setting the derivative equal to 0, because you can find those highs and lows without looking at the graph, right? Without looking at a really ugly graph, okay? I like example 7. What's up? Okay, good night. Go to sleep. Okay, example 8. I do not like example 8. I do not understand what they're trying to get at with example 8 because I have, okay, let me just read it to you. I'm going to change it a little bit. Find the area of the triangle formed by the coordinate axis and the tangent line to the curve of this thing at the point 5, 0. Great. Okay. I can see, now, normally we wouldn't be given the graph, but whatever. I can see that this graph has this little triangle. We're trying to find the area of it. And I can see that the base of this triangle is 5 and the height of this triangle is 2. And to find the area of that triangle, I take 5 times 2, which is 10, and I divide that by 2, and that is 5, right? That thing has an area of 5. And in nowhere did I use calculus. I don't know if they were wanting us to use calculus to find the equation of this tangent line first. But given the fact that I have the graph, like I just graphed the thing and whatever. So let's do this. Let's change this. And instead of finding the area of the triangle, all the things, because I think they were wanting us to do this originally, we're going to find the equation of the tangent line to the graph of y equals 5x to the negative 1 minus 1/5 x at the point 5, 0. We're going to find the equation of the tangent line. All right, we've done this before. We did the whole like limit process thing to do this. And I know for sure that you have a problem like this on your homework assignment. Maybe it's not worded exactly like this, but equation of a tangent line. Equation of a line is y equals mx plus b, okay? And the m is the slope of the tangent line, and the slope of a tangent line is the derivative, right? So I'm going to use this equation, and I'm going to find the derivative. All right, so y prime is what I'll call him. And if I find the derivative, I'm going to do the negative 1 down in front, right? So this is negative 5 x to the negative 2 power minus, here's my constant times my x again, so I just have 1/5, right? All right, I'm going to fix this. This y prime is equal to negative 5 over x squared minus 1/5, right? So that's what he looks like. Okie dokie. Here we go. Now I'm going to, that's my derivative. This is the slope of my tangent line, right? Like how the heck is that a slope though? If it's like a big long equation. Well, I haven't plugged my point in yet, right? I have to tell it I want the point 5, 0, right? Now, y prime, we're not going to plug 0 in for y prime. We're trying to find like y prime is like representing my m in this case. So we're not going to plug 0 in yet, right? We're just going to plug our 5 in. So I've got 5 squared on the bottom, which is 25. Negative 5 over 25, that reduces to 1/5. So I have negative 1/5 minus another 1/5, right? Which is negative 2/5, right? You're just adding those together. That is what my m is. That is what my derivative is at the 0.50, right? Negative 2/5. Okay, so I'm going to bleed over into this part. Y equals negative 2/5 x plus b, and to solve for b, now I plug 5 and 0 into x and y, right? Y is 0, 5 is x, and I have plus b. Negative 2/5 times 5 is just negative 2 if I add the 2 over. B equals 2. So my final answer for the equation, for the whole equation of that tangent line, is y equals negative 2/5 x plus 2. If I'm asking just for the derivative at this point, at 5, right, like just for the slope of this tangent line, that would just be negative 2/5. But the whole equation of that tangent line, if I plug in x and y, is this whole thing, okay? I think they were probably wanting you to do that first so that you can see, like, hey, his y-intercept is 2, he's touching right here, and he's also touching at 5, 0, and now I can use that to find the area, right? Whatever. So they were assuming that we didn't already have the graph. So we're just kind of cheating by doing that way. Anyway, all right, last thing, higher order derivatives. All right, so we have this big long equation. This is this has 5 terms to it. It is a quartic function because he's x to the 4th power, but he has 5 terms. And when it says find f prime of x, that means the first derivative. So first derivative. Okay. If it says f double prime, that is the second derivative. F triple prime is the third derivative. Now they quit doing quotation or whatever those things are, apostrophes. They quit doing apostrophes after the third derivative and they just do F4, which means the 4th derivative, the 5th derivative, the nth derivative, which means like if I would continue this process on forever and ever and ever, what would happen to it? And you'll see how this works, okay? So let's start by doing the first derivative of this thing, all right? So I'm going to start with this guy, 3x to the 4th power. 4 is going to come down in front. Multiply by 3, that is 12x to the 3rd power, okay? Minus, the 3 comes down in front. That is 6x to the 2nd power. 2 comes down in front. That is plus 2x to the 1st power. This 4 times x, this is like x to the 1st power. The 1 comes down in front. So minus 4x to the 0 power, or just minus 4. We know that if there's a constant in front of an x, it's just that number for the derivative. And if it's a constant term without an x, his derivative is going to drop off. Like his derivative is 0. Okay, so now this is my first derivative. If I want to do the second derivative, okay, I'm going to do the derivative of this thing. Okay, so I keep repeating the process. 3 comes down in front. This is 36x squared. 2 comes down in front. Minus 12x to the 1st power. This guy is just plus 2. And the 4 drops off. Okay. Next, you can kind of see right now what's going to happen already. Okay, keep going. 2 comes down in front. That is 72x to the 1st power. This guy will be minus 12. And then the 2 will drop off, right, after that derivative, okay? Next, 72 multiplied by 1, that is just 72x to the 0 power, or just x. The 12 minus 12 is going to drop off, okay? Now, if I'm taking the derivative of 72, that's just going to be 0. And if I keep going, like the derivative of 0, 0, the derivative of 0, 0, the derivative of 0, 0, eventually, no matter what, if I have a polynomial, not something where I have like this thing going on where I have square roots of x's and stuff in the bottom. Like this guy is not going to end up doing the same pattern because this is a rational function and not a polynomial, right? He has an x on the bottom. That's not how this is going to work. But if I have a polynomial, doesn't matter how many terms it has, eventually when I get to the end, and I take the derivative over and 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 over again, eventually I will get to the point where I end up with 0 because every constant term is going to continue to drop off until I have nothing left, okay? That's what happens with polynomials when you take multiple higher order derivatives. Okay? All right, those are kind of fun. I think those are interesting. But it does leave some room for error because guess what? If you screw up on your first derivative, then your fifth derivative is, well, I guess your fifth derivative might not necessarily be wrong. Your second derivative will probably be wrong, though. Your third derivative will probably be wrong. Eventually, no matter, even if you do make a mistake, it's going to end up dropping out to be 0. But some of your other derivatives might be wrong also if your first derivative is wrong. So just be careful going through that. Take your time. But that's kind of how that plays out. All right. Use the rest of the time to work on your homework assignment. I think most of it is finding derivatives of things like that and simplifying and doing all the things. So work together if you need to. I don't care. There you go.